Okay, good morning everybody. We start right away. The first talk is Antoine Jego, creation by parts, and all wonderful things you can do with it.
Antoine, perhaps before you start, just to recall that there will be the television going up at some point, so we do as usual, I think. And then we'll have some eventually a discussion in the garden because they want to film us.
So everyone needs to look really happy.
Maybe I lock the doors. Please.
Okay, so we'll try to be as natural as I can if the TV shows up at some point. So that's the first part of this talk. The second part will be given by Guillaume. Okay, so this audience, and I'm not sure I will give really a motivation about random conformal geometry. So these two talks will be about the SLE and the GFF. Important, I guess. In these two talks, we will try to understand how these types of objects change when we apply, when we perturb them by local conformal transformations. So as you know, these objects are conformally invariant or covariant. So if we apply the conformal map, we will understand them. We will understand what it does to these things in a very precise way. But if we apply a map that is not conformal everywhere, the law is going to change a bit, and so we want to understand precisely what this is doing. Okay, so I'm going to give one application, and Guillaume will give another application. So my application will be about this conjecture by constellation swap. So let me recall. So today I will be mainly focusing on the SLE loop measure. So SLE loop measure. And all this talk will be about kappa less than 4, so we will be in this simple regime. So the SLE loop measure, so this is like a measure on these types of curves. So we have like a loop case. What people are usually more used to is, let's say, radial SLE or chordal SLE. In the chordal case, for instance, you will have like a domain with two marked points, 0 and infinity, and then we have the curve that goes from 0 to infinity. Okay, so this, like on this side of the board, if you want, this is extremely nice if you want to apply tools from stochastic calculus, because the construction from brain in motion is quite direct. And actually, the first construction of SLE by Schramm was in this context here. Whereas on this side of the board here, we have a slightly, like this has a different flavor, and this will be more a static construction, SLE with more symmetries. Here we have a loop. And so we'll try to convince you that in a way, this is also very good for different purposes. And what's the link between the two? So so this one also has an orientation. If I explore a little portion of my loop, so let's say I'm exploring this side of the loop, then the remaining portion of the loop will be simply a chordal SLE in this domain with the two marks.
Let's proceed. Go on.
Okay. So that's the link between the two. And today we'll be really focusing on the one on the right hand side. Okay, so let me maybe start with the theorem. The SLE kappa loop measure is a CM restriction measure on the space of Jordan, on the space of Jordan curves. So I will explain what this result means. So here CM is the central charge, which is given by 1 minus 6 square root of kappa over 2 minus 2 over the square root of kappa squared. So this one is from minus infinity to 1, as gamma goes from 0 to 4.
Why CM?
CM for matter. Okay, so maybe it's... And also in the paper we have another thing called C. That's the M. Okay, so this okay, I will explain in a bit what this is saying. And if you want, this will be like the existence part of this Kontsevich-Suov conjecture, and it has a lot of history. Like I think it would start, let's say, with Loewner, Schramm-Loewner, with the restriction property of further SLE, and the construction of the measure. Started with Wendelin-Werner in 2008 with the case kappa equals h3. So kappa equals h3 is special because in that case CM vanishes. So this restriction property will take an even simpler form. And then Benoit Dubeda, Campanelli-Werner, and finally Jan in 2021 constructed the full measure. And if you want, maybe like in a word, we could imagine that the construction took a little bit of time simply because, like the link between these two types of objects is not so trivial.
By the way, do you have results for the left-hand side?
The results for the left-hand side. So there is so the left-hand side also satisfies some restriction property, which will be of a different type. But I still need to tell you what I mean by restriction property in this context of loops.
Actually, will you tell us what is the SLE kappa loop measure, or will you sort of just...
For me, this picture will be enough if you want. It's a measure, a Borel measure on the space of Jordan curves, so simple loops in the Riemann sphere that will satisfy some nice property, but also. If you explore a little portion of it, you will the rest will be simply chordal SLE in the remaining.
So I just take it for granted that conditionally on a piece of the loop, the remainder is.
Yeah. So I mean, so if you want, I'm not. Yes. Yes. Sorry. So the theorem is due to many people, so that's what I was... Okay, so maybe I can write... Sorry? It's basically the construction of the measure. First Wendelin for kappa equals h3, then Benoit Dubeda for another value of kappa, and then Campanelli-Werner and Dapeng-Jan.
So the theorem is a definition.
The theorem is the construction of the existence of, and basically the construction of the object entity. Yeah.
Just to be sure it's an infinite measure.
It will be an infinite measure, yes. Okay, let me maybe give you the definition of CM restriction measure. Okay, I will have J will be the space of Jordan curves. Definition. So I fix a value of CM less than 1. And let nu be a borrowed measure on J. So J, you can equip J with a very natural topology. Okay. So nu will be, for me later, nu will be my SLE measure. For any simply connected domain D, I will write nu D, d eta. So eta will be a curve. So this, I define this as the restriction of nu to the loops that remain in the domain D, and I'm adding a little twist, exponential Cm over 2 lambda star, and I give it let me put this in red, lambda star eta boundary of. I will tell you after the definition, or the second part of the definition, what this lambda star is. At the moment, this is simply a quantity, a number. Okay. Oh, sorry. Yes, sorry. Sorry. Thank you. So we say that nu is a Cm restriction measure if for all D1, D2, so simply connected, and a map, so my map phi, and a conformal map phi from D1 to D2. Nu D2 is obtained from nu D1 by pulling back nu D1. Okay, so let me rephrase that. I have a measure on the space of loops in the sphere, and I'm defining a notion of restriction to small domains. So I take nu as a domain, and nu D is basically the restriction of nu to the loops in the domain. And you can obtain, these nu D1 and nu D2 are obtained simply by sending the curve to the other. So this is it's a mixture of restriction and conformal invariance. Okay, so now I need to tell you what is this lambda star. So lambda star. So if I have two sets A and B in my domain, lambda star of AB is given by. Okay, there is a formula. I'm not sure this is extremely useful, but basically you take your Riemann sphere and you remove somewhere a little ball of reduced epsilon, and okay, so it will be the ratio of the log of the ratio of zeta regularized determinant of the Laplacian. So here, what do I have? Okay, so let me call this guy O epsilon. So it's O epsilon minus A, the determinant of the Laplacian in the domain O epsilon minus B, divided by the determinant of the Laplacian in O epsilon, determinant Laplacian, O epsilon minus A union B. Minus log 1 over epsilon.
Your Laplacian is Dirichlet?
Yes. Yes. And you can also express this. There is also a nice expression in terms of the Brownian loop measure. a similar type of expressions. This one would be, again, you take this O epsilon, and in this domain O epsilon, you are looking at the mass of Brownian loops that intersects both A and B. And again, you have this normalization procedure because we are in this grouping. Right, so that's the definition of restriction measure. Which explains basically what this result is saying here. And the conjecture is that there is, for each value of Cm, there is a unique such measure.
Well, will you make an historical recap, or because does it the first situation where it appears, was it really related to SLE or?
The first so was it related first to SLE? So this I'm not sure exactly. I can tell you that. So in this context, maybe it appeared in a different setting first, in a causal setting.
But what at Mazarin in the story started to look at this measure, right? Mazarin or in similar context?
Yes, but in a different context actually, and I'm definitely not the best one to tell you what Mazarin did. Okay, so let me write the conjecture. So by Kontsevich and Suboff. So for all Cm, there exists a unique, so unique up to constant, up to multiplicative constant. Cm restriction measure. Okay, so that's the conjecture, and as I said, the existence was proven by a series of papers by different people that I have already mentioned. And if you want, this really gives a different perspective on this SLE, because before we were looking at SLE as growing curves that are built out of some Brownian motion in some dynamical way, whereas here we are really viewing SLE in a slightly different context, in a loop context, but more like as a static object. Okay, and so the theorem that I want to explain a little bit today, the theorem with Guillaume, is that uniqueness holds.
So if you don't remember Mayer, perhaps you can recall why it's important to have this restriction property.
So as I said, you are really viewing SLE in a different, in a completely different way. So for instance, maybe if you want, I can give you two direct applications of this uniqueness result. I guess it will motivate a little bit why we care about this. So when you are growing SLE, there is a clear direction. You are really going from 0 to infinity in this radial case, or even in this loop context. In this loop context, the curve, it is oriented. So the fact that the law, if you forget about the orientation, the fact that the law is invariant under reversing this orientation is not clear a priori. So it would be, so here in this loop context, it would be saying, that if you exchange 0 and infinity, this is the same. Whereas when you have such a characterization, this is just clear because you are, in a way, you don't care about the orientation of the curve. So this is the reversibility of SLE. So reversibility of SLE was already known before, of course. But if you build SLE from this dynamical construction, it's a non-trivial fact. Whereas when you have such a characterization, it is just clear. Another application, a direct application, would be the duality between kappa and 16 over kappa for SLE. Because you can take the so SLE loop measure, it turns out that it also makes sense for larger values of kappa. So you can take a kappa between 4 and 8 and look at the boundary of some special component. And this one, you can show that it will also satisfy the same CM restriction measure, and you can use that to obtain like a three-line derivation of this duality between SLE 16 over kappa and SLE kappa. So maybe that's, I don't know if this is convincing, but yes.
I'm trying to wrap my head around this measure. So is there any interpretation of lambda star? I understand Gaussian loop measure, okay, but why should I take this particular
value of lambda star?
Yes, why should I care about this measure?
So that's a good question.
I'm asking.
Yes. But okay, I mean, the fact that in the end you recover SLE tells you that this is the right thing to do.
Why
you could, like a priori, you could also put different values of lambda star.
Different functions.
Different functions. This is definitely something that you can try.
So is this the only functional that will give you this?
No, I don't. No, it's not the only functional that will give you a measure.
No, that will give you a measure with.
But it turns out that this gives you like maybe the most natural measure you can hope for. But,
why did they care about it?
Why did they care about it?
Yes.
Yeah, I think they had they really had a different. And like in this paper by Kontsevich and Swaff, I'm not sure that they even mentioned SLE, or maybe they mentioned, but yes.
Maybe it's like you can use as a motivation, for instance, the fact that if you consider unicyclic forests in a domain, then you're going to get a cycle somewhere. And that's the construction by Benoit and Ubeda, right? If I'm not mistaken.
Right, but.
And that will correspond to a certain value, non-zero value of C, the central charge. So maybe this is good enough justification that it really shows up naturally.
And from a CFT perspective, reweighting by the determinant of the Laplacian is something that people want to do. So.
Sure.
Is it for percentile manipulation, like you're doing the Gauss now?
Yes, so there are path integral interpretations of this measure.
The interpretation.
In this interpretation, the action is the determinant of the jump operator across the curve, and this is related to the scalar potentials on the universal Flesch space. So it's very canonical in a sense.
Yes.
Also add the original formulation of contribution scope to some more general setup with partition functions of CFTs, and that somehow good by this conjecture. For any CFT, if you see some interface curves, then you get this measure.
Just understand what happens if you put CM bigger than 1?
So if CM is bigger than 1, then you are just outside of this realm, and it's not clear that such a measure would exist.
Okay.
That's basically the problem.
And
I think what we did with Guillaume, maybe it would give you the existence of a measure, but it would not be. It would be like a complex measure, not a probability measure. Okay. And right, and okay, but I didn't really want to mention this path integral formulation of SLE. Okay, I can say more words about that, but okay. So let me mention that there is recently a new proof of this. So there is a new proof by Sai and Van Gao in 2025. in the regime where the value of Cm is between 0 and 1. This is more counterintuitive. And now, okay, now the rest of the talk, I will try to explain a few words about the proof of this. And yes?
As it's high and low, they also show that the restriction measure doesn't exist when C is larger than 1.
Maybe. This I don't know. But maybe they did that for a different context actually, because indeed they show some optimality results for some regimes, but I'm not sure it concerns the SLE loop measure. It might be for different measure actually. Right. So, but yeah, indeed it has this flavor that if Cm is larger than 1, then this is not possible. In any case, it's not expected that you can construct such a measure for Cm is larger than 1. Okay, so sketch of the proof. And okay, so to me, really, this talk is more about the proof in itself than the result. With Guillaume, we ended up showing this at the very last stage of our project. We were not at all motivated by this conjecture initially, and we were more motivated by what I'm going to explain now. So, okay, so we will show that conformal restriction. The conformal restriction property implies some integration by parts formula for the SLU loop measure. And here I would like to mention the work, so see also the work by Maria Gordina, Wei Qian, and Yilin Wang. In this paper, they also do this step, if you want, which is to really obtain this integration by parts formula. And from this integration by parts formula, we will be able to obtain some orthogonal polynomials which characterize the measure. So if you want here, this is more like an analytic step where we do computations. And here it's more like an algebraic step where out of this integration by parts formula, you want to derive some special families of polynomials. Okay, so that's roughly the plan of the proof, and now I'm going to explain the plan of this proof in a very concrete example. So I want to explain how we can use such a strategy in the context of the Gaussian distribution in dimension 1. So if you want, what I'm going to talk about now is a baby version of Stein's method. So Gaussian integration by parts. So here you can think, so I have mu is a measure on this measure that we all like. And I want to characterize this measure in dimension 1. And I have this integration by parts formula. How do I want to write that? And x will be a random variable that follows the law mu. And so for any test functions f and g, so here I have f prime. I write this as an integral, then I'm applying my standard integration by parts formula for with respect to Lebesgue measure. So I would integrate f and differentiate g times e to the minus x squared. So when I do that, I will have two contributions. So I obtain x gx minus g prime x. So you know, this part here is when my differential hits the exponential. So there is the minus x that goes in the bottom, and this part is when the differential hits g. And this is what you get. That's the Gaussian integration by parts. And okay, so let's say that you manage to show something like this, and you want to prove that this formula characterizes entirely the Gaussian distribution. Of course, there are plenty of ways of doing this. One way that is related to our approach is you introduce the Hermite polynomials. So h0 equals 1 and hn plus 1. So you basically take this term here. So I define this as x. Okay, now x is my little x if you want. Little x, hn minus hn prime x. Okay, so these are the Hermite polynomials. If I plug f equals 1 and g equals hn in the formula above, on the left-hand side I have 0, because the derivative of 1 is 0. And on the right-hand side I have 1 times hn plus 1. And so I obtain that the expectation of hn plus 1 of x equals 0 for all time. And so, of course, this entirely characterizes the Gaussian law. And what? So we'll try to use some strategy like this in this context. And as you can see, we recognize two steps. The first one, which is really to obtain this integration by parts formula. The second one, which is a little bit more analytic, algebraic, where you want to construct polynomials, and you need to say, so here what was important is that, the Hermite polynomials, they span all the polynomials. And so in this simple example, this is quite clear, because you can directly check that each polynomial has degree n. So in our context, it will be a bit more subtle, of course. And also what I want to say here, and Guillaume will emphasize this much more, is that these integration by parts formula, they give you, they give like a rigorous meaning to these path integral formulations, because here what they have in front of the x is really the derivative of the action. So you know me. So here, of course, since I'm in a finite dimensional setting, my path integral is rigorous. So this is my Lebesgue measure, and it's e to the minus the action. But in general, these integration by parts formula will make sense, and they will give us like a rigorous interpretation of these. Okay. So if we want to make this work, I first need to explain to you what I mean by differentiating in my space of Jordan curves. So I'm going to introduce a notion of the derivative. So, I have a curve, the Jordan curve eta, and I want to perturb it slightly. So before, I'm going to always restrict myself now to the Jordan curves, which separating 0 and infinity. So I'm fixing two mark points 0 and infinity, and I'm simply asking that my curve separates these 2 points. So here I have 0, and here I have infinity. And I want to perturb this curve slightly. phi t of theta. And the very natural way to do that is you start with a vector field. So we take a Laurent polynomial vector field. And I'm considering the flow associated to that vector field, which will be equal to z plus t z plus phi dot t. The flow, the associated flow for t, for complex values of t that are small. So here, I might have a singularity at 0 and at infinity. So concretely what it means is that I will have a small neighborhood of 0 and a small neighborhood of the origin. And outside of these two small neighborhoods, my maps phi t will be well defined for small values of t. In particular, when v if v is equal to 1z or z squared, here phi t, I'm just recovering the Möbius maps. So which are, of course, the conformal maps measurements here. But for different values of v, I will have more general maps that are not conformal everywhere on the sphere. And they will be actually conformal everywhere except in these possibly like neighborhoods around 0 and infinity. So in general, phi t is a local conformal map. Okay. And when t is 0, phi t is just negative. So phi t is really a way of perturbing the curve in the direction b. So the lemma, which is about the existence. Okay, so let me try to look at the order of. Yeah. So the lemma, there exists a dense subset C. So a dense subset of L2 of nu. Okay. So nu will be my SLE kappa loop measure. Restricted to J0 infinity. So there is a dense subset C of L2 of nu such that for all vector field V and for all F in C and for all eta.
Can you say what is C of Z?
What is what?
C of Z.
It's the Laurent polynomial, so it's
Okay.
Z to the n
And that ensures that there are no self-intersections.
And
if you start from a Jordan curve, you do not have self-intersection. For short time.
For short times, yes. For short times.
But the time may depend on the curve. Right?
The time may depend on the curve. No, so really what I'm doing. So T, I'm not sure you should think of T as time. It's more like.
Okay. T is the parameter of the population.
Right. So T is a parameter.
The parameter depends on the curve.
No.
It's a diffeomorphism.
Diffeomorphism. Okay.
I really map the whole thing with the same factor. And I'm only and the curve. I'm never really looking at the time parameterization of my curve. So
That's okay.
Okay. And so here I'm just I mean, it's the existence of derivatives. So if I apply f to a perturbed eta, so phi t of eta, what I recover is f of eta, of course. So first of all, see the derivative in the direction v, plus t bar another derivative in the direction v, plus little of t.
Antoine?
Yes.
Can I just check? This is really new, is really the SLE-kappa loop measure or some a priori measure satisfying the...
So here I'm taking SLE-kappa loop measure, but you could take any measure that satisfies this CM restriction measure.
Okay.
And that's the only property that we need.
Okay. So any
measure.
You don't even need the restriction property. Really have operators on this space.
I mean, at this stage of the lemma, yes. Because what I'm defining here is, okay, what I'm doing here has nothing to do a priori with the SLE loop measure. It's only a result about differentiating the space of Jordan curves. But we don't care about that. You can think of this as mu is any CM restriction measure. And so here, this result is about the existence of derivatives in this space.
Is there an intuitive explanation why you get two derivative operators instead of one? LB bar?
I mean, so here it's simply because you are differentiating in a complex space. So I mean, it's really like if you have if I have a function f from C to C that is differentiable, then I have two derivatives. So it's the same here. Is this result clear? And so now really LB will be my differential operator in the direction V. That's it.
I have a question on
Yes.
notation, sorry, I'm lost. So F is the...
So F is a test function. F is a test function.
So that C is L2...
So C is a subset of L2 of so F belongs to that.
So f is a function of the
F-
Jordan curves.
The function on...
So F takes the Jordan curves
To C.
to C.
Yes.
F is a test function. In R here would be saying C would be a subset of differentiable functions. And F is a differentiable function. And here I'm perturbing slightly eta by a t amount in the direction V.
Do these operators preserve C?
And these operators they preserve C. At this stage, I don't think we really care. And map C to C. Okay, so now I can state this integration by parts formula. Theorem.
So what's that LB?
LB is my differential operator.
It's defined by the letter.
It's defined by this. Defined by this lemma. So with Guillaume, but also Gordina, Schramm-Loewner. So I want to state my integration by parts formula. So for all vector fields V, the L2 of mu adjoint that I will denote simply by LV star of LV is given by, okay, so there is a formula. LV star is equal to minus LV bar. So LV bar is this other guy, plus, okay, some explicit thing, Cm over 12. The Schwarzian derivative of f minus 1 paired with V minus the Schwarzian derivative of G minus 1 paired with V times identity, if you want, where okay, so I need to tell you a little bit what this is. So where so this is my curve theta, which separates 0 from infinity. F is a uniformizing map from the unit disk to the interior of the curve that preserves the origin. Oops, sorry. G is the same thing outside. So this is G. So this explains what F and G are. Cm is the same. V is my vector field, and here, this is simply a residue bearing. So you would do a contour integration basically anywhere far from the origin in infinity. Right. And that's it. That's the integration by parts formula.
And so for this, you need the mu is a restriction measure.
Exactly. So actually, this result holds for any CM restriction measure. So that, yes.
What is again? What's the differential operator? What is LP? What's the definition of the?
What's it?
What's the definition of the differential operator? The LP.
I mean, it's defined here.
But at this stage, it might still depend on the measure, right?
What, the LV?
Yes.
Ah, no. LV is LV is I mean it's an operator that has nothing. I mean, so this is defined. If you want, I could rephrase this by saying, let me tell you exactly what this space C is, and C would be like a space of smooth functions, if you want. And then for each smooth function that does not depend on u, I have such an.
I see. So what you're saying is that there is this subset C actually does not depend.
The subset C does not even depend on u.
Okay.
Actually.
Okay.
Right.
So this lemma you could get rid of depending on mu, and you could say, and there exists this LV.
Yes. But it
And
was.
then you also want to make the point.
But I also want
exactly.
I also want to make the point that these differentiable functions are actually dense in L2 of U. This is important. And this is important because otherwise there is no way of characterizing the measure. The set C is not dense.
So in the theorem, nu is what exactly? Nu is an
you can think of
at this stage.
At this stage.
Arbitrary restriction measure.
Yes.
That satisfies the restriction property you mentioned.
And we will see, because I will try to give you one little explanation. So how you can derive this integration by parts formula from the conformal restriction property.
So when you say it's an adjoint, these are probably unbounded operators, right?
Yes.
So you mean like a formal adjoint on the
So
common
here,
domain?
here I would the adjoint I would say for any test function f and g that are nice.
Common core.
This relation holds.
What happens at the moment.
Okay, so proof. So actually with Guillaume we have a different proof. So I mean, as I said, this result is proved in these two articles, and actually the two proofs are a bit different. So wait. Okay, so first what we do is, we are interested in a measure on loops that remain in the entire sphere. First we do a limiting procedure by saying if I am in the sphere, then I must remain in some extremely large disk. So let me call this disk now, I will call this disk the unit disk. So this is the unit disk. I have a curve eta in here, and I'm perturbing slightly my curve eta in there. And I want to understand what happens here. So first, by using some conformal map, you can perturbing the curve eta amounts basically to perturbing the boundary of my domain D and fixing the curve eta. So what I'm saying is that D fixed and eta perturbed roughly is the same thing as eta fixed and D perturbed. And okay. So now I will fix eta and I will change a little bit my domain. So now this domain will be phi t of D. And I want to understand what does this thing do on my curve eta when I'm changing a little bit my domain D.
Should be phi minus t maybe.
It's fine.
What?
If you want to move eta by phi t, it should be the same as moving
D
by phi minus t.
Ah, yes. But let me not call phi minus t phi t.
We change v into minus v.
Yes, that's possible. But I don't want to keep track of this here. I mean, this is more like a high-level proof. Now the point is that so we want to use the restriction property at this stage, and this restriction property will hold if the phi t is a strict subset or a subset of D. And so for this we use so we will assume that V is Markovian. So this is a notion introduced by Guillaume and co-authors. So what does it mean V to be Markovian? So for certain values of V, it turns out that phi t of D will be a subset of D when t is positive. Or actually, if t is even in a narrow cone where the argument is small. And these Markovian vector fields actually generate all the vector fields. So this is important. So there is no loss of generality by assuming that V is Markovian. And now, when phi t of D is a subset of D, actually we can use the restriction property of the measure. So the measure in the domain phi t of D is actually absolutely continuous with respect to the measure in D, and the Radon-Nikodym derivative is explicit, given by this lambda of D eta phi t of the sum. So here we use the restriction property. And so now the computation boils down to evaluating the derivative of this guy at t equals 0. And so now it's really like a Brownian loop measure computation. Okay.
So do you have to choose B such that there is no singularity in the matrix?
Ah no. You it's important you allow singularity in the unit disk.
How can you write in phi t of D?
Okay.
The domain inside.
So here, yeah. So I mean, it's the interior of phi t of S1, if you want. Yes. Okay, so that's all I wanted to say about this integration by parts formula. Now, So the question is, now that you have this integration by parts formula, what do you do? Yes? 5 minutes, yes. In any case, I'm not going to write anything else, I think. So,
How do you go from this to
what? From this to here? So, I mean, okay, so I try to give a high-level proof where you want to differentiate in this space J, so you want to perturb a little bit the curve. I try to convince you that this amounts to perturbing actually the unit circle, and so in the end you want to compute the differential of this Brownian-Loewner. And this one will involve terms of this type. But I mean, but here I'm not doing the computation. I'm just trying to give you the root. Yes.
But for me, I'm also a bit confused by this. So the only way this adjoint depends in nu, depends on nu. I mean, LV does not depend on nu.
Yes.
But the only thing that depends on nu here is the space with respect to which you are computing the adjoint.
I mean, so this one does not, LV does not depend on nu. The adjoint depends on nu. The adjoint crucially depends on nu.
Right. So, but how is this reflected in what you're? This is what I want.
But that's the whole point. Like we are, like I mean, this result is saying there is a unique measure. So the fact that the adjoint, when you read this formula, you do not see any dependence in nu is a crucial point of the proof. And the dependence in nu is only reflected by the fact, you know, that you have the CM is a crucial parameter here. You can read it in this formula. But a priori, the adjoint depends on nu. And the fact that this dependence is only via this parameter Cm is a good indication that indeed there is a unique measure. And now you have this integration by parts formula. You want to show that that this characterizes entirely the measure, and so you are back to this Hermite polynomial story. You want to build a family of polynomials out of this formula. Show that you are able to compute the moments associated to these polynomials just by reading this formula. And show that indeed the polynomials that you have constructed spans all the set of polynomials, and this is a non-trivial fact. This really relies on representation theory tools, and basically it concludes the proof.
Can you recall what are the assumptions that make this term doesn't depend on nu?
What are the assumptions for what?
I think that this term, well, okay, this term does not depend on nu for sure, but when you compute the adjoint, you should use a couple of assumptions that make you sure that you don't depend on nu in the end.
So I could rephrase this by saying
yeah, that's not the general fact.
No, but he uses it. Nu is a switching point.
So you mean that
nu has a switching property.
So this formula here, I would really what this is saying is that for a family of test functions f and g in a given space, I'm not telling really what this space is, but that this formula holds for these test functions f and g. And where here I would replace this LV star by that formula.
That's a general fact.
No, but this is what I'm saying. I'm replacing. Let me replace this by explicit, where explicit is given by this formula. And so when I write this result, this theorem here, what I actually mean is this. And that's it.
That's not my question. Then,
that's not your question.
Okay, you compute an adjoint for any measure, any measure in the world.
Yeah.
You have the adjoint exists, whatever the domain. So here the point is that your integration by parts does not depend on you.
Or it depends on you only via CM.
Yeah, sure.
It depends on you, like the restriction, no?
Everything is in the random decoding derivative actually. So
But I was thinking that maybe the invariance under conformal mass is important. And the
yes, but that's what allows you to write this random decoding derivative. So now if you look at the expectation of
Okay, so this formula here you use the invariance under conformal maps.
Yes, but this,
and what
but this is I think this is actually hidden in the definition I gave of restriction measure. I mean, in particular, a restriction measure is conformal invariant.
But the fact that you have this random Nicodim derivative is not enough because you can have in front. If you take any two arbitrary Dutch measure and you define them as a
With this lambda.
So lambda is a specific.
I could take any. I could multiply this density with any measure in the world. I won't have such stuff here.
Ah no.
I just take exponential of lambda of eta times any measure. I won't have such a nice formula. Well, that's my question, in fact. So I rephrase it. Take your lambda.
Yeah.
Define exponential of lambda times any measure in the world on curves. Do you get such a clean formula?
But
not get this.
I mean, you would need
So,
you would need a
that's
consistency property and so on.
So my question is, what do you need exactly? What do you use? Or beyond this density here, you use the conformal maps and what else?
So conformal maps and this restriction property, and that's it.
That's it. Okay.
Yeah. But, and also the fact, I mean, also this limiting procedure. Okay, actually, it is hidden in this restriction properties.
But for the first part, so to show that d fix and eta perturb, that you can change them, that comes from conformal invariance?
Yes.
So that's where you use conformal invariance, you use it there and then you use it.
Yes. Okay. Yeah, basically, conformal invariance will allow you to fix eta and only move the boundary.
Okay. I think we can have more discussion over the break. So thank you very much.
In front of the black